What is the definition of aerosols? Quickly आप बताएंगे तो मैं accordingly talk को orient करूँगा अभी time duration को देखते हुए. Suspended?
Solid or liquid? Solid part.
You are excluded. So there are particles on this table. What is that? So that is dust or aerosol?
Depending on the size.
But particle ending here is dust or aerosol? You are confusing me here also. Aerosol. All aerosols can be dust or all dust can be aerosol?
All dust.
Okay. Mic भी है क्या?
The mic.
सर आपको mic भी है? ये move कैसे होगा? Okay. So I planned the talk.
तो बड़े वाले से आगे पीछे होंगे।
थोड़ा इसको समझा दें। भाई कुछ प्रॉब्लम है इसमें आगे। ये पीछे करता हूँ तो आगे जा रहा है।
तो ठीक है।
नहीं अभी भी आगे जा रहा है।
तो भी आगे
अब कहाँ से?
क्या हुआ?
मैंने करा स्टार्ट।
नहीं जा रहा है।
तो बनाया था वेट किया वो जा रही है
कहाँ से जा रहा है? आगे जा रहा है।
करो करो
ये आगे जा रहा है। Okay.
शिवाजी आप बैठ के सर का जो है स्लाइड जैसे वो बोलेंगे आगे पीछे पहले शुरू के स्लाइड में
Well, I express my thanks for inviting Sweta for taking paid and helping so much.
फर्स्ट करो we can start
Professor would there training the session. Professor Walia from education. Thank you so much. Since time is short, so what I am going to do, one thing to note, dust includes both the particles in suspension, particles on surface. But aerosol includes only particles in suspension. That's one. Second is, quite often, and I see that there are people from Pollution Control Board here, there are requests, sir, metal analysis कर दीजिए. कौन सा metal? तो पता लगा कि मेटलॉइड का नाम ले दिया. शुरुआत कहाँ से करते हैं? आर्सेनिक से, कैडमियम से. किसमें करना है तो उसके बाद फिर वो अगला सवाल होता है कि आप कैसे करते हैं. Now you are going to a shop and asking him what is there in your shop, that accordingly I will buy. So that is a frequent experience which I encounter. I have been encountering, and some of them, Veer Kumar as a company manager is encountering that I need equipment which can do this. So he has to fabricate for that. So we'll talk on that point, that how do we choose a technique? How do we, what points we should be careful? There are two aspects here that define the objective of the work. Define the objective of the work, and the story begins with that if you say air monitoring, the pollution control board, you have to report. So that means you are doing a monitoring study. There is no science involved into that. And the pollution agency is asking you the data and to follow the guidelines. They have enforced certain guidelines. You cannot deviate from that also. So you don't have much choice. But when you come to the science domain, you are free. So the instrumentation, the sampling, all protocols will depend upon what you are looking for. Two are entirely north and south poles. Then research domain. So if you are looking at the air quality, then you have 7 criteria pollutants, and all details are given here. You don't have to use your mind. Follow the document. 8-hourly, 24-hourly, height, instrumentation, flow rate, method. Every damn thing is written here. You don't have to do any exercise. Just go to the CPE site. You will have a document. Right? You can download those who don't have, and those who are from HPCC, DPCC, or JKPCC, they can give you. They will ask that, sir, I need the 7 criteria pollutants. These are the numbers, these are the methods. If you adhere, give me. Otherwise, go back. It is as simple as that. And again, so these are all from the Pollution Control Board. The methods are set. Right? Now, coming here, please go back. Please go back. Okay. Forward. So now the current problem out of the 7 criteria pollutants is about the particles. Rest we have enough control, good control on their inventories, their trajectories, their control measures, their impacts, catalytic converter in place, oxidative, reductive, etc. So the current issue is with the particle. The particle is bekabu. It is not in control. From where it is coming, and you look at this figure, which seems to be easy. It's not that easy. That people are talking nanoscience, right? Nanocenters, a discipline itself. But look at it here in the atmosphere. It is a nanofactory. If you convert this micron meter, how many of you know that why this axis on log scale? Raise your hands just. This axis is log, not by mistake or by choice. I am forced to follow this log scale. Why? So these are complex systems, so you can talk to Ankit also after me. Right. So these are the processes which makes the particle complex. I said that it is bekabu, we are unable to understand. These are the processes, these are the size spectrums. If you can go back, from 0.002 micron to 100 micron on a log scale. Log means 10 integrations, not 1 to 3 integration. So that, and the other interesting point here is, you always must have heard in catalytic chemistry that finer particle have larger surface area. Am I right? But if you look at this, the number is higher here, the surface area is lower. I leave these questions open. You can talk to Ankit, he can explain you, or you can talk to me over phone later on. But the point is that these are the complexities with the particle, which you see a particle, that the number is higher here, the size surface area is higher here. Even in the marine air, not only the continental, in the marine also. This produces a complex chemistry, which you see a solid particle, which we observe a particle. There's so much, emissions, absorptions, oxidative reduction, growth, nucleation, condensation process take place. It's not that only something emitted a particle. If it is emitted, then certainly by science has evolved, we can find out the source. But now it is not emitted. It is evolved, it formed in the atmosphere by coagulation, condensation, gas which is coming at hot air vapor, getting condensation, making a particle in the nanosize particle range. That they collide, right? Grow in the size. So that makes the system complicated. And the residence time accordingly. Now people say residence time is not only the particle is there up and down. No. The particle was emitted and it transformed there. So that original particle has lost its lifetime. So when you are sampling, you must take this into account that you are doing a sampling for 8 hours and the particle is a lifetime of 1 hour. You won't be able to capture it. And you will say that I didn't get this particle because the particle lifetime is over. And this depends upon the transport, growth, and chemical processes. When it comes to science, then these are the issues which you encounter. You are doing a sampling for 24 hours. The source is only operative for 1 hour. Now 23 hours additional sampling, you have diluted the whole, you won't get a signature that yes, there is a burning, but in my sample it is not there. Because you have diluted it. You have unwanted, unnecessarily, carried on 23 hours. This lifetime is not there, you won't be able to capture it. So these are the points you should consider. Then the meteorology, which is not in your control. My control or your control. it goes up and down. This roof height of this room is fixed, but outside this roof height is not fixed. Technically, we call it as planetary boundary layer or mixing height, and then manipulation coefficient of 6,000 meters square per second uh, using wind speed. So this moves up and down. Now, if you bring this down, my voice will become louder. If you raise this up, my voice will be audible in the air. Same happens in evolution with these particles. That mixing height goes up and down. So accordingly, the concentration of the particle, the composition will keep on changing. And here is the idea that 2.5 kilometers in the summertime, you are approaching summer now. And in winter, it will 500 meters. 5 times change over. So you can think about that volume is changing. So how it will going to yearly basis. This was the one which we did in Diwali. Clearly visible that this should go down with the height. It goes down in 2 dimensional, it increases, lapse rate, positive becomes positive, then again goes up. So this effectively becomes a barricade for the pollutants to disperse. They accumulate there, stagnate there, only horizontal dispersion. Now in the circumstances, the source remains same. It did not change, but then the lapse rate changed, so the net outcome in your sample will be changed. So you have to consider this while looking at it. Suppose your mixing height has gone so low. For example, in Diwali day, it becomes 50 meters in Delhi, and you are sampling at 55 meters in a balloon or in an automatic sampler or sensor, whatever device you use. There is no use because this atmosphere is closed at 50 meters. So you have to consider this point. Then the estimates what is missing in the particle which I said, the same is written here in the text. Now you can sample everywhere, all the time. It's not possible, it is not water that you go and take it seasonally or yearly or soil you take, it will remain same. It's a dynamic system, keep on changing day and night, rural and urban. Noon chemistry is different, evening is different, night is different, season is different, yearly is different. Resources, electricity, high-end instrumentation, power, consumables. It's not possible. So inventory is a technique. Now the inventory is also having a lacuna as far as the particle is concerned because it is not a source. Inventory is done for all possible sources for all pollutants in a given time area with a fixed boundary. Now here there is no source directly. So they are linking the secondary component in inventories and there are errors and confidence limits are much poor. Confidence limits are much poor. Activity data are incomplete because activity is happening in nano size range in the atmosphere. You don't have a registered source, identified source. Now this need in advancement, that source diversity, and you can consider that pollutant is conservative. Means that it stays as it is emitted. It is non-conservative. And non-conservative when you cannot see, it is not your control. So that component has to put in the models and think about it beyond the box. That how do I add these parameters so that my inventory is correct? The measurements are not possible at all. So now when you come to the measurement, there are a variety of things. One of my students did this work and showed the full intelligence whatever he could do in the faculty in Vishwabharati. So I don't know these many techniques, but he made me for it. So there are so many techniques available. Now what to choose, which to choose? All have their own pros and cons. Scientific domain, output data plus the input money. How much you plus? You choose what you want to do. What is your objective? I will be only talking about the gravimetric methods and how to proceed in the analysis part, data generation, and the parameters which you should consider in mind. Because like in the morning, the facility was shown that you can download a form, fill it, send your sample to the instrumentation, pay the money. That's one job. That's not a complete job. Now, what is your sample? Which method you will digest? Which machine you will use? Which standards you will use? If you don't tell all the things, the another party will take the money in the bank and give you some number which you play around, be happy. And in that case, if you follow that approach, you will be better publisher. You have more research papers. I tell you. So I don't like this business of paying money and getting analysis done. That man is paid, he is a technician, he has no affection to the data and the sample. He just put, there are students, there are people who are coming, sending the samples by courier. And this man sometimes feed the sample in the machine, sometimes makes the data and send it to you. And you are happy. So don't do that. Don't do that. Take some necessary precautions. Things are complicated and easy also, but once you understand them. So again, these are the different components because it is also outside. Now this is the one with the climate just to have it. That why do we talk about climate? The human race is most greedy and the most, highest form of the life, which doesn't respond unless until you hit an individual hard. If I am hit hard, I only wake up. Otherwise, I say, how does it matter? So the climate is impacting everyone, and the other aspect of the particle is the inhalation. So I am affected by the pollution in the room. Climate changing, I will be affected. My welfare will be affected. So therefore, this particle in question is in demand, is in focus, not nationally, internationally. And the other important point that somebody must have said, but then it makes sense to me to say, share it with you. This is plus, this is minus, and this length is telling you error bar. So if you look at this plus and minus, one may end up saying that there is no warming and no effect, net is zero. Plus is equal to minus. Warming is equal to cooling. But in the component of the particle here, mineral dust plus as well as minus. We don't know. This is IPCC report. And these are the error bars. That again, the inventarization I was saying, that there are errors in the data, the confidence limit is low. So we have to work about it. If you look at the chemistry, so some of the elements which we do for our interest, for our purpose, but ultimately what Professor Tripathi said, the story begins with that every damn material is taken from the crust. The global diagram per year data tells me that natural sources of particles in the ambient atmosphere are much more than the anthropogenic. But you cannot control that, you can only understand that. So if your all material is dominated by the crustal material, then you have to have a background which Professor Tripathi informed you, now share with you, that what is geology. So first primary is everything is natural, and then you are adding. It is not that you are producing directly in the particle stage. That's exclusive case specific. But in general, the ambient atmosphere, all elements which are there identified on the crust material or soil or surface dust or sediment or rock, whatever you call, is there in the particle. All. But all cannot be done. There is another question, I throw it open, that he was talking about the concentration, and then some abundance and some pattern, and at the end he said ratios. Now I don't know why he used ratio word. He didn't use isotopic concentration. I leave this question open to you. That whenever you talk about isotope, you talk about ratio, not the concentration. There is a logic behind it. Think about it. See, these are the issues that the students come sometime. Sir, वो strontium-87 का concentration चाहिए. बताइए मैं कहाँ से लेके आऊँगा? And he is adamant. He will bring some publication also. Sir, इधर हुआ है. So you have to have the perfect background of the concept of the knowledge. Then only you move forward. And if you have a clear knowledge and understanding, and you move forward. Take my experience that to whom you are approaching, he will you help more than required. But if you don't have, then he won't help you, whatever you require. Forget about more than that. So these are the some chemical abundances in percentage. Again, I have taken from CPCB side, student probably. That there are elements, different elements, soft, light, alkali, alkaline, earth, metal, D block, E block. I preferably don't use this word metal. Somehow I don't like that. So I use the word element. So different like abundance. Now not necessarily that this element is there, it is only qualified. Which I can have multiple sources also. You are not on a specific. So generally if you develop it, then you say exclusive sampling you do around the activity. and then you have a signature, then you say that this is this, this, this. But not necessarily you can pin down. That's another drawback I said to papers, not mine, for the participants who are interested to study thorough papers. They talks in the abstract itself that roughness of the data, improper sampling, and improper selection of the marker elements. So very careful choice that which marker you element you choose for what activity. And then this is the research the author is sitting here that I'm also involved currently. And then the purpose is different, not that why I'm showing my research. That we do modeling. Modeling, you have an algorithm, you have a computer, you give input data. Now, whatever you give input, it will give you output. You can play around with the input. You can make the computer fool. Just playing on the numbers. So when your science and your interpretation is dependent on these graphs, the figures, the science which you must take out of this, which would mean the input of the top of line quality, then only output will be realized. Otherwise, the computer doesn't know algorithm is there, you give the data input, it will give you output. You can interpret, nobody's dying. There is a difference between a doctor and a scientist. By wrong research, nobody's dying. So you have freedom to do that also. Wrong interpretation. That is my interpretation, it's very wrong. There's nothing wrong in it. So therefore, with that, because there is nobody's life is going, so we are using also, that's what we practice. When you have to depend on this output, then input must be important. Then only it will move. Like this is the Shweta's work. Now you give these numbers that this is resuspension. This all depend upon the elemental analysis. If your data is correct, then only this information will be considered correct. Otherwise, it is a beautiful colored graph with some numerical numbers. So the input is very, very crucial and important. These are the equipments. Now, there are equipments. Virji may tell you, I have not interacted long time with him, and there are available in the market that somebody would say, sir, this will do online VOC, online metal analysis, every damn thing is online. But what is the reliability of that online? What is the purpose of that online? What is the cost input to online? Where to install? How to install? They are still broader questions. Not everybody can afford, and they don't also sell to everyone. Right? So, one common method, including the criteria pollutant requirement of PCB, is the gravimetric method, sampling and digestion, and reaching out to the numerical number. Again, I go back to the same question that what is the objective? What is the collection method you will take? First your objective, then the collection method will come. Well, what is your accuracy of the data with the objective? Like when I talk isotope and I give to general party, he will talk to me in 6th decimal. Before I reach to 6th decimal, he will not talk about it. The numbers आपको भी दिखाए थे इन्होंने, they are at 5th decimal. Probably his were 6th, I think, he did it in Germany. But in India, even 6th is available now. So before 4th, 5th decimal, he will not consider it. So level of accuracy and what digit you want. It defines your objective, methodology, and the subsequent processing of the sample. If you have, I give you another example just came to my mind. You have 10% something, you make it 11%. Change by 1%, the relative error is 10%. By changing the composition 1%, your relative error is 10%. If you have something 100 ppm, you change it by 50 ppm, your error is 50%. So addition of 10,000 ppm is marking to 10% error. Addition of 50 ppm is marking to 50% error. That's the level of accuracy precision we talk about. That how do you handle the data? आप लिख देते हैं ऐसा होता नहीं है हम गलती कर देते हैं जो recalculate करते हैं तो catch हो जाता है. There are catch mechanisms also in the data. It's not a very difficult thing to do. So these are the points again taken because of the paucity of time. I am reorienting the talk. Whenever you are talking about the ambient atmosphere and pollution control, follow the guidelines. They are binding actually. These guidelines are binding. right? But researcher also can take a cue from there. There is no harm in that. Like when you talk about the ambient atmosphere, your sampling height should be 4 to 12 meters, somewhere between 4 to 12, depending upon your topography, geographical location, and the shadow zones, wind direction, etc., etc. And these points, researcher also the site should be representative. आप कहाँ सैंपलिंग कर रहे हैं, किस एरिया को रिप्रेजेंट करते हैं, आप अपोजिट टू विंड डायरेक्शन खड़े हैं, then what to do? There's no meaning. This smart choice industry does it. The pollution control members here, they are well aware about this. Please don't mind it, take it on a lighter side. When they go for review, the wind direction is from west to east and the source is here. You sample it here. A perfect sampling, perfect data, there is no pollution. Mass. Because you are behind the source. You are all this is going pollution, what to do? So site, that's what they check. When they inspect, surprise check in the data, that's what they check. That all these parameters are adhere into it or not. Comparability represented as topography and physical requirements. You should have a light, power connection. Security. Instruments are what 10 lakh, 20 lakh, 50 lakh. Security. Manpower, trained manpower. Like I have been working, I'll show you photographs. So I have to hire the trained manpower in Jaisalmer, in Itawa, and a number of places where I will work. Because I cannot be everywhere. I cannot be everywhere. और आपने छोड़ दिया तो ऐसा भी होता है कि वो this is the real experience. तो सैंड लिया, उसके ऊपर फिल्टर पेपर पे डाल दिया और आपको दे दिया फैक्ट्री. Rather than telling you कि लाइट नहीं था उस समय और लाइट का बिल भी ले लिया आपको 10 रुपए यूनिट. These are the ground realities which we encounter in the field. क्या करोगे आप? So this is another interesting thing. I am told all are aerosol scientists, but still reviving, revisiting things also is better in life. The hair in your head is much coarser than the particle in you. So with what size you are playing, you are talking, you should be keeping in mind. That size of my hair is much bigger than the particle of PM2.5 or the salt grain. So that kind of a, data quality you have to maintain. You have to play with a very, very, very fine particle. Now this is another point that we were doing this. Then we went to PM10, then 2.5 and 4. Now a broader question for the scientist. If you are pollution, then PM10 and 2.5 is a binding. You are collecting 2.5, the definition says the particle of 2.5 micrometer or less at 50% cutoff diameter. That's the standard definition. Is that right? Now you come up with a chemistry. In that chemistry, say XYZ is higher. Tomorrow I do another chemistry, same site, same location. I say ABC is the chemistry. What has happened? What has happened? That the definition says 2.5 or less. Now, this is also less. If you say less than 100, 90 is also less than 100, 1 is also less than 100. That's a typical question which you should address. You won't be able to track the sources, the secondary robustness in the AI, you won't be able to bring it. Because you say less than 100. Now, I have 90, so I'm pretty good with definition that so less than 100. And he is working on less than 10, so he's also good. And Veer Kumar says I am working on 0.1, so he also is correct, less than 1, less than 100. Now, all three are different processes, different chemistry, different instrumentation, different science altogether. So that's where the data for the scientific domain, now people are breaking the size fractions to understand the sources. You got my point clear? Did I make some sense? That 2 is also less than 2.5, 0.1 is also less than 2.5, but which is dominant size? Now, once you collect it, you can't know the size also. There's no technical. It's not a dry powder that you do scattering and get a particle size. So the background study, the data, time to time will tell you that how do we move forward. Same one. So accordingly, you will select the equipment and after the equipment first site, then the equipment, then the substrate to move forward. Now these are the real data that 35% is PM10, less PM10 in the total, And within this, you look at it, the different size fractions where I work, that it depends upon that which size fraction is, dominant. Accordingly, we'll get a data in this, that 2.5 you consider 36 in this 10, 36% is 1 micron. So roughly 40, if you consider this also 1.5 makes 50. So I am studying PM10, but the chemistry, the particle size is dominated by 1.5. So 1.5 to 10 to there's dilution only. So when comes science, you take this. These are the model distributions which you encounter if you segregate it in the size. This is myself working in the year 1999. अभी मेरे समझ में आया नहीं पूरी तरह से उसको, still I am struggling hard. So these are the equipments which are available. Please don't use them henceforth. आज के बाद ये जो है ना आपका, और ये जो मैनोमीटर है जो आप प्रेशर डोज लेते हैं, this is totally a wrong choice. It was a forced choice, obvious choice when the science was not there, availability was not there, money was not there. Don't use henceforth. You put a filter paper, you mark it the 1.2 meter cube or 1200 liters per minute. After 24 hours, the lowest point is 0.8. There is no lower than that. Otherwise, it will go down. And tomorrow you take out sample and you take 1 meter cube average. Now you do not know how many minutes it was 1.2 and how many. So your data is highly erroneous. I never used this in my life. Fortunate enough to have a supervisor who gave me at that point of time mass flow control device. So these are the other. Now these are the selections from the market you can do. So selection is depend upon what you want to do, whether monitoring or science. In the science, the mass flow control devices. These are the cascade impactors, various. I won't get into it. Now here you have to think about it. This all is science. This all is money. The money ranges from somewhere where is this glass fiber, I think 100 rupees per day per seat, to some 400, 500 rupees. And here if you reach number 5, it is 2000 rupees a seat. One seat will cost you 2000 rupees. So all are different purpose. No, don't get aspire that I want to use 2000 while if you have money. If your objective is not that, don't use it. All flexion substrate all have different meaning. You want to simply calculate the weight, or you want to do carbon analysis, or water analysis, or you want to isotope analysis. Depending upon the scientific content, you choose the collection substrate. This is very, very important. Like you have done the good sampling, very good sampling, but you use this Teflon filter, and then you say, I want to do carbon analysis. You have money, you got fascinated, and you use this. Now you say, I want to do EDXRF analysis. You can't do it. So the choice of collection substrate is very, very important. It is this is what I have been using, the mass flow control devices. Here, what I do, I show you one term quickly. That's it. I don't want to get into this principle. You can read it: centrifugal forces that the air gets in. It strikes here. This motion sets in. This is the inlet. This is the correction substrate. So the height is tuned in such a way with the flow rate that only PM10 will get into it. And after that, I will further segregate it like this. So I am currently working on this size flexions. I don't talk about air quality. I don't work on that. So my domain is this. If I use 20 cubic feet per minute or 40 cubic feet, if the flow rate is low, I can go up to 0.41. Now with all these samples and one base plate, one set of sample is costing me as on date almost 9,000 to 10,000 rupees. All are quartz. Even I go Teflon, some of them, then it will be 5,000 to 6,000. So this is a science domain. That collection substrate is very, very important which you choose. Now these are the some filter papers. Okay. Now here is an important point for the researchers, because air pollution तो आपको CPC भी force करेगा. You don't have any choice. That W2 minus W1 divided by the V, and that's a way of representing the mass data in microgram per meter cube. So denominator is V. If V is not correct or V is changing, your all data will be changing. That's where the difference between a geochemical approach and air quality approach. But when I review papers, I just do recalculate within a 5 minutes and I can calculate the data is up to the mark or not up to the mark. I don't use the word fake data. Is it mark or unmarked, and then I accordingly take a call on that. How it happens, I just show you that these are the two samples, one and one. Mass composition is absolutely same. Absolutely same. So I have two samples, absolutely same composition. I would say they are coming from same source. Is that right? But if I change the denominator by changing the number of hours of sampling or by changing the volume of the sampling, these numbers would be changing on 0.03 to 0.024, 0.0041 to 0.0031. Now the differences are small, but when you convert, look at logically in a percentage terms, the error is huge. So the denominator is very, very important, that this volume of air, if it is constant, both then will be same. But if the denominator changes, then two samples will appear to me different because the volume has changed. What? Why? One day there was power for 4 hours, other day it was for 24 hours. There is nobody's mistake. The mistake is the recording the data. Data logger was not there, you didn't have a correct information. Analog is missing, you don't know. So if you show two samples which are actually same, they will appear to you as different chemically. And factually you see that it's different. But because you have wrong information, you divided wrong data. Like this, they should fall on a tie line. So what do? In such cases, you normalize the data of the same sample with the same element. So the internal effect is offset. Internal effect is offset. Enrichment factors, like I gave one example, the concentration, I divide by aluminum here. Any metal you can use, titanium, this iron even people use. Divide by this crust by crust. So the internal offset with reference to the one element will be done when you take the enrichment factor, irrespective the volume was different. So these samples showing to you S1, S2 as different. When you talk about enrichment, they will be offsetting it. So you have to be careful when you look at the geochemical or air quality wise. But once you don't produce the data in terms of geochemical, you don't understand, you won't have any sense that what has gone wrong. Only the one who knows he can recalculate, go back. He can go back. Then the digestion comes. So we have a microwave digestion system. Now something is visible in front of your eyes is always better than what has been heard. That's the difference between the microwave digestion and open display. Open as it means you are watching it from your eyes. And I would say that if you are a good analyst, environmental scientists are best analytical chemists by the way, because they will play with the natural material, unknown material. So if I see something that's open digestion, or if you hear something and interpret, that's the microwave digestion. Because the vessel is closed, you give a microwave command to it, radiations to it, 2450 hertz, and then you develop pressure also. Now the vessels are there. What is happening in the vessel, you don't know. And I would say the best one, that every damn thing which you have comes in the solution, clear solution. Whatever I had, good or bad, I don't know, but it has come into the solution form. The spectroscopic techniques, wet techniques are most preferred and best way of analyzing particles as on date. So you have to rely on that. So if you're constrained, you have clear solution, you can go for it. Like in open acid digestion, the silica is removed, so time is actually extremely hard. This is what we have been doing. We have modified yourself, but this way they have a volatilization problem. The volatiles will go. I will use HF, so SIF4, SIF6 will go away. So I won't be able to do SI analysis. There are constraints also, one or two. And if you are interested in the elements which are saying that some students also does come, and it comes to our mind also sometimes. Let us do zircon, let us do PZ group of elements, let us do RE. It doesn't happen that way. They will require different digestion protocols, fusion also. Even open digestion micro will not help you. You have to put the flex. So different techniques, HF. I'll give you a paper to Smita, he can share with you. This work is from this work. I'll go here. Okay. These are the methods which are accepted methods in the literature. Any of you can choose. So these are the dilution methods, these are the fusion methods, lithium metabolite, sodium hydroxide, sodium peroxide. And for PG elements, like if you are interested in platinum, then you have to go for nickel bead formation fusion system. Okay, this is the one very important point, that open acid digestion, low TDS, because part of it, generally Tripathi showed you 40 to 70% is silica on an average. अगर part से तो 99 चला जाएगा. So 40 to 70% आपने operate कर दिया. So net dissolved load is low in your sample, which is a requirement of the instrument. You cannot put in every damn thing there. There is a restriction, and detection limits are low. Here it is a disadvantage that of the open acid dilution, because you are using HF, HCl, HCl4, refractory phases will not break down. They will not come into the solution, and the time consuming also, cost is low, pollution also takes place compared to the micro-closed digestion, where you have TDS is reduced. If silica is removed, like people are using boric acid and then remove. Otherwise, in closed vessel, nothing is going out, no evaporation. So if you want to take it out, you have to take out after digestion chemically. But cost is there, rapid, etc., etc., low blinds. Fusion method, I won't get into it. Okay. Now QA, QC. I'll take another 15 minutes I have with me. So I'm only sharing with you, which I like that the researchers should share with me later on when they ask for their answer. That's the whole plan of the talk. At what points you should consider it when it comes to research. So generally reviewer writes, editor writes, they provide QA QC data. Now we wonder what is, unless until I was knowing, I read it, I also didn't know. When I started PhD, QA QC was not in a place, these terms were not there. We used to have accuracy, precision, repeatability, standard deviation, representativeness, recovery, these terms were there. But this is an offshoot later on, it came QA QC. So it's nothing, you just read it. All actions, procedures ensure representative, integrative service. They should be recorded. You should record all events which you are doing. That's assurance. And integrity of the sample, accuracy and reliability of the analytical result. You have to assure me that I use this balance, I use this clean air, I use these acids. Now you are talking to me on 5 very frequent point that a student will come, sir, 2 ppm cadmium. Sir, 0.2 ppm arsenic. And the acid which you have used is written on the bottle how much arsenic cadmium it has. So that itself will come into it. So I have to be reliability of the data. When I use in my laboratory, I use distilled acid. I distill the acid, and then because perchloric ultra pure is not possible for me, it's a high cost. So those quality control is actions that monitor measure the effectiveness of film. Now you decide this, and then the actions which ensures this, one after the other. That's the key. So continuous improvement. Everyone involved is responsible. In a laboratory, you cannot say I'm not responsible. Everyone is teamwork, stronger customers, clear about each person's responsibility, clear communication, operate all these points. When an instrument fellow like Veer Kumar, a manager comes, he will talk less about the instrument, more about this, because this is how he controls his QA/QC about the instrumentation. The same should be done with your data. And the first point begins with clear recording. In fact, the data which I was reading and asking him, they were my PhD data, which I collected samples in 99, which generated isotop data now. So I could interpret my data book, my field book, that sample was taken on which time, which height, which place. That makes you quality control and assurance. Nowadays, sometimes a reviewer also asks, give me the PDF file or give me a photocopy, scanned copy of your field book. ऐसा भी हुआ है, मेरे साथ भी हुआ है. That he asked me, there was a dispute on the calcium barium line on AS, and he argued with me. I said, whatever fact is fact. I sent him the PDF file. He said, I appreciate your recordings and everyone, but I still don't accept the paper. I said, that's okay. But the point is clear that he asked me the data because there is interference between calcium and barium line. This is a monochromatic beam of light which is coming, and you choose a lamp light with the system, but each element have multiple lines in AS also. So you have to be careful which one you are choosing. There will be interference. You will be happy that I have given a monochromatic light, but that light interferes chemically with someone else also. Maybe first order, second order, third order, not necessarily first order. So those points are coming into the, point. I want to go into this. Okay, this is the kind of data which Rakesh produced during his MPhil. You look at 6 samples he collected and 6 others, digested them as 12 samples, 6, and plotted on a tie line the quality of data. You look at it, bang upon the equiline. That tells you the sample collection was okay, the digestion was okay, the analysis was okay, efficacy of the digestion system was okay, precision and accuracy was okay. You have to achieve this. That's how I check with my students. I give them 2 samples without telling what are they. If it is perfect, they will fall on the tie line. That's how, otherwise they can mislead you. So I randomly give 2 samples, 3 samples without telling what is that. So that's how we check the quality. This is the new system we are adopted now, Kumar. We have been capturing photographs because this instrumentation is a too tedious task, too costly. It's not possible. So the cameras, CCTV cameras which you have, we are taking snapshots. The camera rotates 0 to 180-degree angle. Take 6 snaps during one rotation. After every 15 minutes, and the algorithm is developed how to interpret that image, transform it to the PM 2.0. This graph tells you that the predicted and the actual with the photograph. That's the new point which started with the ISI Calcutta. That the photograph based. Now algorithm is made, it is tested, then automatically it will be giving you the numbers. Just photographs. Okay, now I have to move forward. That spectroscopic techniques, interaction of matter and energy. Now, if you interact that, there can be scattering, there can be absorption, there can be emission. These are the processes which can happen. So, accordingly, you have instrumentation in the morning showed to you. Emission it can be absorption, it can be spectrophotometer, it can be spectrometer AS or ICPOS or mass spectrometer or light scattering. These are the processes which can happen in the, and they are the one which most frequently used in the environmental science, including geosciences. So again, there are some constraints given by the agency which gives you the control agency, pollution control agency I'm talking about. That they give some instructions, some advice, guidelines that which elements or which filter matrix and which method you use. But in research, you have freedom to choose the equipment based upon the ability, precision, and accuracy required by you. So in general, now look at it, so much bulky. I don't know. People are writing mercury, titanium, antimony, molybdenum. Now molybdenum analysis writing doing by SCMS looks very nice and fancy. MS also. But it's a very tedious talk. Very tedious talk. Identifying, I am giving 1 or 2, 3 examples to you to make some sense. AS is the most suitable element. When to choose, how to choose, I'll take there and then put it out. Okay. Now again, the way I said that define the objective, how to choose the instrument, what is the nature of the sample, how many samples you have, right? How much time you have, how much money you have, what is the accuracy you require, what are the chemical interferences supposed to be with the pre-background information and the detection limits desired. So these are the various equipment. Now you report the data, I have done 0.2 ppb or 1 ppb of lead in the aerosols. I will calculate the mass in that, I will calculate 1 ppb and I will consider that you have diluted in the method by 25 ml. I will calculate the dilution factor and go back that it is beyond the detection limit and a comment that it is not possible, this data is not reliable. That's easy to calculate, I can go back. Whenever you say that this is the concentration, knowing your procedure, I can go back and what is in the, so there are 2 aspects here. Concentration in the sample and in the solution. You report in the sample, in the dry powder, in the solid particle. But you didn't analyze the solid particle. You put it in the solution. So you made a dilution. So what is effective concentration in the solution that should correspond better than the detection limit of the equipment. That point you have to take care. Otherwise, whatever you do and the paper gets rejected with these comments, you feel bad. So initially you have to do this homework, you have to smart enough that whatever I am reporting must be 3 sigma up than the detection limit. Must be 3 sigma up than the detection limit. So this is the wet technique, neutron activation, XRF, ICP-MS. Now I'm not going into the principle of the machine, but how to select, because machines you cannot buy, you have to explore and then see where you can do the analysis. So selecting the analytical method will depend upon these are the fact things for me and the important one and for me for the discipline. Accuracy and accuracy. Sample amount. What is sample amount? ml, liter, 1 gram, half a gram, 0.01 gram, 0.02 grams. Accordingly, we'll choose because that will lead to the in solution concentration and the detection limit. Concentration range. It doesn't operate that you go to an instrument and you operate from say 1 ppb to 1000 ppb or 100 ppm. No, it's not going to work. Metrics of the sample, number of samples. You have 100 of samples and you want to do calcium analysis. I would say go for spectrophotometry. It's not bad, but people don't go there because it's spectrophotometer. I don't go to ICP-MS. Not advisable at all. It depends upon number of samples, number of elements. Right? Throughput कितना है आपका? Speed is skill and cost of analysis. Machine है आपके पास, operator नहीं. Cost नहीं, gas नहीं है आपके पास. If you have ICP-MS, you don't have a good quality argon, it's not going to work for you.
Yes, sir.
So XRF when to choose because XRF में क्या होता है कि आप सैंपल दे देते हैं टेफ्लॉन फिल्टर पेपर पे एरोसोल में और डेटा आपके पास आ जाता है. सबसे आसान काम यही है. इससे आसान कुछ है नहीं.
Sir, I would request you to talk more about ICP-MS because we are having it
Okay.
downstairs.
So in this, the point is that the sample. Remember, all analysis which we do in environmental sciences, they are reference analysis. You are measuring my height with a scale. You must ensure your scale is calibrated and perfect. Only then you can tell my correct height. The least count of your scale is in inch, then you can tell me inch. If it is centimeter, you can tell my height in centimeter. If it is in mm, you can tell my height in mm. This is what the analogy goes with the analytical science. Your scale, your reference, your standard. So in the XRF, that's the biggest problem to getting the standard of the same nature, same metric, same quality. These are the couple of ones available. Okay. So don't think that this is the worst machine, it is the cheapest to the costliest one. And don't think that this serves all the purpose. The arrows have some overlapping period here. Now if you look at it, this is on the right hand side, far one end, this is another end. That means that somewhere this is the only usable, in some sections this is the only usable. So one instrument will not show your all problems. That's another difficulty they are getting in producing the data. None of them can help you in standalone solving the problem. If you want to use this can overlap with this much, but some part this will do. Suppose you have two machines, this one. So this is a common part. Some exclusivity stays with here, some exclusivity here. And this is as good machine as others. One mistake I have committed and I apologize deeply for that. This should be spectrometer. This is a overlook from me because the students made it and I apologize. Don't repeat it. I categorically teach the students spectrophotometer is only for UV visible because photo light it works. Rest are meter, like car meter readers basically. Right? So I apologize for this mistake. Overlook at my end. So spectrometer, mass spectrometer, not spectrophotometer at all. So this is the one which you see the dilution, how you move from here to here. Dilution constraints, single to multi-element, sequential to simultaneous. You have 3 ml sample, you want 30 elements. This requires in ml solution 10-15 to develop a color. It is color-based technique. Here Lematla. This is also 3 ml solution, one record monochromatic BL law, so it can give you data of one element analysis at a time. So if you have total 3 ml, so these two fails here. You have to move here. So this is the arrows how you detection limit from higher to lower and lower. Sensitivity, how much the system is sensitive. Ear sensitivity that you can hear the noise from here. I make a lip movement, you can only see and say that yes, movement is there. I say something, you can say you are saying something that I cannot interpret. When I say something and you reproduce it, that's how the noise, the limit of detection and limit of quantification are. 3 examples I give. Noise, Now, it's noise happening outside. I can't interpret what they are saying. Right? So that becomes noisy. And then limit of detection when you can detect that I'm speaking. When you can reproduce that, I would say that you can quantify or reproduce power. So every time standard deviation has 3 sigma linkage. So these are the points which decides your linear dynamic range. That line, then heavy elements, then separation constraints. A reference material, well-established substance properties which are sufficiently well established by multiple techniques, multiple labs, multiple persons, offsetting all errors. And any reference material which you use, remember it will have error limits with it plus and minus. If it doesn't have, it is not a reference material. It's not a. It will always have plus minus because the definition says which are sufficiently well established by multiple methods, multiple laboratories. So that means there is always standard deviation working on average stability. And then CRNs, the metric should match. Now, flow is different, soil is different than the coal fly is. So you should have a standard like this. Anthropogenic aerosols in urban area should have a different one. Plant should have plant, animal tissue should have animal tissue, milk should have milk. The matrix should match. Then only we move forward. Okay, the precision, bias, sensitivity, and concentration range. I won't go into this. I am told to talk to you about this. Okay, I'll talk here. That instrument must be calibrated with the standards. Now, when the instrument calibration is done, another 5 minutes, that you give the concentration, the instrument only reads that and gives a numerical number which you informed with the instrument. Instrument have no sense at all. It's working on your command. If you say this is aluminium, he will read as aluminium. If you say this is 5 ppm, he will say the 5 ppm. So choosing a standard and feeding a correct value is your first job. How to calibrate. The plot is constructed between a graph of instrument signal. It can be absorption, emission, or conductivity, or emission, or scattering, whatever, and the analytic concentration. Is run if response is within the LDR. You calibrate and the dynamic range you decide. If it is within the range, then only this number will make some sense, otherwise no sense. And closely depends on the matrix. If matrix imprints are low, calibration curve methods are okay. But if the matrix are different, the calibration is not going to work. You have made this line, that line, standard method, internal method. Okay, this is the data which I generated between 2 equipments, magnesium on atomic absorption and magnesium on ion chromatograph in solution. I could read up to 0.9. See, students come with the data on water soluble fraction and some trace elements, making this graph as 0.99. They forget that the acceptable error is around 20%. When you are talking on PPP level, the international acceptance level is plus minus 20%. But he or she deliberately wants to put it 0.999 and reducing the error to 1%. That itself brings the data in down. Because you cannot attain that. So this is what I did with the analysis at this range in the blood serum. This isotopically labeled standard addition method I use, that I determine the mass, but I labeled another with another standard, which the isotopically. So once I get a peak at C12, I will always get a peak at C13 also. So that will tell me the data is in control, and this is what we could achieve from 1 ppb in the blood. If your clearest lines are like this in control, then only you can move forward. So last is that when you talk about ICPC saying, another 2 minutes I will take maximum. That
So your food has been packed.
what is the flow rate? Right? Signal and signal to background ratio. Now signal is equivalent to SPR ratio, but background is going down. Background is going down. So nebulizer and seed gas flow controls the amount of sample introduced as well as speed, thus the residence time of the sample in the plasma. So when you say this analysis on ICP-MS, you have to think about to go to the literature, what the seed gas I want, what the nebulizer flow I want, because the analyst will tune it for his own purpose. Like Shweta is using, suppose I am using. I tuned the flow rates to my own requirements. For your, it may not work. So it will depend upon this parameter. Then this is the low resolution and high resolution. That signal to background ratio. What happens? that when you are checking on the signal, there is a peak coming like this, and your focus is on the peak only. Then the next time when this peak comes like this, you will be more happy. And of course you should be, because the numerical number is also high, peak height is also very high. Please don't do that. You always, along with that peak height, focus on where this line is moving. You have increased intensity by 10 times, but background increased by 12 times. So signal to background ratio is dropping down. You have to maintain signal to background ratio starting from the calibration to the end of the analysis. Peaks keep on moving. Definitely they will be merging, resolution may interfere, the chemical interference may appear, and then this peak height may go up. And you may have some number, but then you should focus on that what the background in the particular sample. That also it will lift it up. These are the critical points when you are go for analysis. You should be careful producing the number. That's what I am doing. Now here is the standard deviation with the integration time. More integrations, lower relative standard deviation. It depends upon which integration. Now one would say, sir, then we should always go for 30 seconds because it is giving low RSD. It is not in your hand. You are constrained with the gas, with the elements, with the solution amount. So you may have to choose somewhere. You have to choose somewhere. It doesn't work well for everyone. Then the instruments have the dynamic linear range, like this is the range which I did. And if you extrapolate this away, how far it will maintain the linearity, that will be dynamic plane. It will not move to infinity as a linear line. It will fall down like this. So within this, you can operate within the linear dynamic range up to which you can maintain the linearity. Now this is the spectrometer resolution. There are 3 peaks here. There are 3 peaks here, and there are 2 peaks here, because the resolution is less than 10 picometer, and this is 10 picometer. So it cannot resolve. It cannot mark and show you 1 peak. As on date, the resolution we have achieved, I think 7 picometer we have gone down. 5 picometer is also available. So if the lambda values are different by 7 picometers or 5 picometers, you will have 2 peaks. That is the reason. Now you are choosing this. This instrument is not giving you this line. You are giving the number that which wavelength you want to have emission. So if you are giving some number and that coincides, you don't have a background of the resolution power of the and the other elements, the emission lines, they will overlap with each other, give you 1 peak. They won't be able to resolve that. As the name is resolution power. So how to resolve it can do adjacent lines, that will depend upon. So this is your choice. You have to give the command. Not me or Shweta will do. You will ask a person who is asking the analysis that which lambda you want. Then the sample is standard. See, now there are 2 different lines. Doesn't work correctly. It has to maintain on 1 line. Energy transfer, variation of instead of sheet gas and the debolization. So optimization has to be done. I am stressing upon that limit of detection and limit of quantification, 2 are different. 3 sigma thumb rule you maintain from noise to the detection to the quantification. And then with that 3 sigma further, I would say that your data is correct. And you can achieve that. Already noise 3 sigma, then detection 3 sigma, that is quantification. And then in the quantification 3 sigma, I will consider your data is good. These are the parameters which you should take into account. Now you look at this how this analyst has tuned up the machine. It's not that machine is doing something. Analyst is playing around with the machine and tuning it. Multiple peaks here to arrive at single peak. Is to optimize the flow rate, the argon flow rate, the forward power varies between 800 to 1500 watts. Flow rate, argon gas, cooling, plasma height, all these parameters you have to think about it. Either you take help of literature, try them, or you yourself won't calibrate it. But this is how if you are able to put analysis, then you can make the clarity in the peaks like this. Okay. So I leave with this slide.
Thank you so very much, sir. I want to share with you that at present, Hari facility is not open for outside samples. But now we'll be making this format whenever we are taking any samples. We'll keep all this in mind, what you have suggested. Thank you once again, sir. Now I would request chair of this session, Dr. Walia, sir, to honor
Anybody want to ask
Professor Sudesh, sir. Yes, if you have any question.
Couple of small questions if they are here,
Before I leave, you can ask.
if they are.
I will request Professor Dhar to honor Dr. Walia for chairing this session. Meanwhile, you can ask the questions if you have in
Yes,
mind.
yes.
Sir, I think you can go down now.
I'm winding up my shop.
Okay.
In the meantime, you ask.
Sir, your shop has already been packed
Acha, you-
separately. We will.
Yes, anybody wants to ask anything?
Thank you.
Please ask. This is not fine.
Thank you, sir. Thank you once again. With this, we close the session and lunch is ready downstairs. But before that, you can have interaction with our eminent speakers. I once again thank Professor Jayant Tripathi, sir, and Professor Sudesh Yadav, sir, for taking out time for us out of their busy schedule. Thank you very much, sir, once again. Thanks to all the participants, of course, but that I will keep doing.
No questions? No questions. All understood or none?
Everything is understood. गाड़ी तो लिया आपने?
Okay, we'll take it. Rakesh, you have to bring this board. You have to bring this board out.
साहब का ये ले जाओ।
Right.